Okay, welcome everyone. This is separation process course. Today I'm going to continue the Ponchon-Savit method. So this is the second part of Ponchon-Savit method. We are still talking about multi-stage. We have many stages, and binary system. We have two components, and distillation, which is a method of separation based on the difference in boiling point. So let me summarize what we have did in the previous video. What we have did is that we say that we have this graph, this is the enthalpy, and this is the composition, and we have the enthalpy curves. Okay, and also we say that we need to specify where is my xd and where is my zf and where is my xw, and then I need to specify where is my OW, okay, and where is my feed point. For example, let's say I have a saturated liquid feed, so my feed point will be here, okay, so it will be here. This is my feed point. Okay, or for example, if I have a vapor Q equal to 0, so my feed point will be here, okay, or if I have saturated mixture, my feed point will be in between. Okay, so let's suppose the case where we have a saturated mixture like this. Okay, oh sorry, this is OD, this is OD here, it is not OW, this is OD, the top section operating point. Now let me specify a new point called the OW. OW has the same idea as OD. Okay, so it has a set of coordinates x and y. The x here represents the xw, and the y here represents hw. So I'm talking about the enthalpy of the liquid waste, minus qr, the duty of the reboiler, over w. Okay, to make the analysis easy, we don't have to determine this coordinate. We don't have to. There is an easy way, which is by connecting. So you have, this is OD and this is the feed point. If you connect this 2 point until you cross XW, see where is XW? It is here. So this is XW, this line represents the XW. If you cross this XW here, this will be your OW. OW represents the bottom section operating point. Remember, distillation column, we have top section and bottom section. So this is OW operating point, and this is OD, and in between we have the feed. Okay, so the intersection between this line, because you know that to draw any line I need 2 points. So if I have OD as I determined from previous lecture, and we have the feed point, okay, so I can easily determine the OW point, okay, by the intersection with XW line. Okay, so this will be my OW. Okay, so now how we can start the solution for this type of problems. To start the solution, first we need to start from the distillate point. Okay, Where is the distillate point? It is here. If you have liquid distillate, which is the case for total condenser, your point will be here, right? Because this line is for liquid. And if you have a vapor, it will be here. Suppose I have a liquid distillate, so this will be my starting point. Okay, this one. Okay. So how I can proceed with the solution? The first step is, you see here, let me explain it. I have here the condenser, okay, and either if I have total condenser, this will be liquid. If I have partial condenser, this will be liquid. If I have a partial condenser, this will be vapor, and this is always vapor. Okay, if I have total condenser, in order to go to this vapor, okay, how to go from liquid to vapor? If I have partial condenser, the state will be also vapor, so I can start directly from here. Okay, but if I have here a liquid, how to go to this vapor phase? Simply, I can draw a vertical line. So by drawing this vertical line, I go from the liquid phase to the vapor phase. Okay, so at the end of the day, I will stop at this point, okay, which is at xd, okay. Now, how I can continue to determine the number of stages? I need the equilibrium data. Remember that we said that the Ponchon-Savit method relies on three things: the equilibrium relationship, and the material balance, and energy balance. We applied energy balance to determine the OD point, and we applied the material balance that help us with the energy balance, and also we apply it to get L and D and W. Okay, remember that F is equal to L plus D, and ZFF يعني ال component material balance, which does to multiply each one by the mole fraction ZF X. Sorry, I will do it again. You have the feed, and this is ZF, and this is the condenser, and this is the reboiler, and here DXD, here WXW. So we say that F is equal to D plus W, and ZF F is equal to XDD plus XWW. So if I know ZF and F, and I know XD, XW, I can determine D and W using these two equations. So we can seek a help from the material balance if we need L, if we need, sorry, not L, if we need D and W. Okay, so now the last thing is to apply the equilibrium relationships. In order to apply the equilibrium relationships, we need equilibrium data, right? The same equilibrium data that was either determined experimentally, or we can determine it using the relative volatility. Remember, if you have a constant relative volatility, you can construct this table by yourself, as we discussed in the previous lectures. Okay, so at the end of the day, we will have this equilibrium data. So we need to benefit from them in order to determine the required number of stages using the Make-Up-Delay method. Using the Ponchon-Savit method. Okay, so how we can benefit from them? Simply, we can benefit from them using what? Using a second graph. Okay, so we need a help from a second graph. So this is my original graph that we have discussed before, and below it I need to draw another graph. This graph will be the equilibrium graph xy, okay, which shows you have the 45-degree line, and using the equilibrium data you can plot the equilibrium curve. Okay, and here in the top you have the enthalpy curves. Okay, and we say that let's say that this purple point represents the xd, and this yellow point represents zf, and this green point represents xw, and we'll say that we have here the OW, and the OD operating point. Okay, and if we have the feed point here, so we can connect a simple line between them. Okay, and the cross with the XW will be my OW. Okay, and we say that we start with this XD, and this will be my starting point. Now what we are going to do, we need to use this equilibrium curve. How we can use this equilibrium curve? This equilibrium curve can be used that if you know x, you can get y. You know x, you get y. Okay, so these two graphs, you need to have the same scale for the x-axis. So if this x-axis for the first graph, this graph, if it is 0, 0.1, 0.2, 0.3 until 1, the second graph need to be same, 0, 0.1, 0.2 up to 1. Okay, so what we are going to do, see, we are going to move vertically until we reach the 45-degree line. Okay, then after we reach the 45-degree line, we know x now. We know x. We are going to move. Let me explain it again. The first thing is that we are here. Where we are here at the black point. This point, is it in the vapor line or in the liquid line? Of course it is in the vapor line. Why? Because it is in the top line. Remember when you say that the top line is H capital versus Y, and the bottom line is H small versus X. Okay, so we are on the vapor phase line. On the vapor phase line, this black point, since it is vapor, so this represents Y. Okay, so how I can know X if I have Y? I need the equilibrium relation. See that equilibrium curve, it represents the relation between Y and X. So if I know Y, I can get X. If I know X, I can get Y. Okay, now we know Y. We know Y. Okay, how to get X? We are going to move vertically until we reach the 45-degree line. So when we reach the 45-degree line, we are going to move horizontally. Why? Because when we are moving horizontally, we are moving at constant y that we know. So we can read a new value of x. See, if you move from here to here, x will change. Okay? That's why we are moving horizontally. So we keep our knowledge of y constant and we move horizontally to get the new value for x. Okay? So once you get a new value of x, we are going to go back to the liquid or vapor. Of course for the liquid, because now we know x, and this line represents h versus x. Okay, so we are going to go to up to the liquid curve. Okay, so we start from here, we move downward until we reach the 45-degree line, then we move horizontal until we reach the equilibrium curve, then we move up until we reach the liquid enthalpy curve. Okay, so at the end of the day we reach this point. Okay, now we have 2 points, first point, second point. We can draw a line between them because you need only 2 points to draw a line, right? So we will draw a line between them. Okay, so this line will represent a tie line. What do we mean by tie line? Tie line means a line that connects vapor composition with the liquid composition. Okay, connecting vapor composition with liquid composition, this is a tie line. Okay, so now we utilize the equilibrium relationship. Okay, so this is the first step. Okay, then what we can do when we stop at this point, we will connect this point to OD here on the top. Okay, so let me do it in different color, in yellow for example. So see, we'll start from this point and then connect it to OD, and then we stop. Then we see we cross the vapor line at this point. Okay, so now we are going to do the same thing that we did in this point. Okay, so we will see this point I have here. I am on the vapor line, so this is why I move horizontally until I reach the 45-degree line. Then I move, this is vertically. I move vertically until I reach the 45-degree line. Then I move horizontally until I reach the equilibrium curve. Then I move vertically until I reach the liquid line. So this will be my second point. Then I connect these 2 points again, this point and this point, my starting point and my end point. Okay, so I connect them again. Let me draw it again in the purple color. Okay, so that's it. So this is the second tie line. This is the second tie line. Then again I will do the same thing. I connect this point with OD point. Okay, and let me do it again in yellow. So I connect this again to the top line. Again I will get an intersection with the vapor curve. Okay, so I need to do the same thing again and again. I start here from the point of intersection, go to the 45-degree line, go to the equilibrium curve, and then go back to the liquid curve, and then connect the starting point here with the end point here again. And let me do it in the purple in the purple color, so I connect them again. A very important thing that you need to notice here is that, see this tie line, it crosses the black line, which is the feed line. I cross the feed composition. Once I cross the feed composition, this means that I go from the top section to the bottom section because I cross this feed line. Okay, once I go to the bottom section, I cannot use OD. I have to use OW for the bottom section. Okay, so starting from this point, okay, yeah, I cross this ZF. I cannot do this. See, take this yellow line. I cannot connect it again to the OD. That's wrong because I crossed the feed. So now I will connect it to OW, this point. I'll connect it to OW. Okay? And when I connect it to OW, I extend the line until I cross the feed, until I cross the vapor line. Okay, so again, I cannot connect it to OD. No, I cross the feed, so I connect it to OW and extend this line. Because I have 2 points, I can extend the line all the way for the whole graph. Okay, so the intersection here with the vapor, I do the same thing. I have this point. Okay, so I move here until 45-degree line, then I move to the equilibrium curve, then I move up, so I reach here to the liquid curve. Okay, again I connect this point with I connect this point with the starting point where I move, yeah, here, this point. Okay, so I connect them. Okay, the question here is where to stop. We stop once we reach XW. See this green point? We say that this green point represents the XW. See this green point? Yeah, this line represents the, let me do it in green. Yeah, this line, green line, represents the XW line. Okay, so once I hit this line, I stop. خلاص, I reach, this is the end. I reach XW, the composition in the waist, so I stop here. Okay, the question here, what's the number of stages? Is it the purple line or the yellow lines? Of course it is the purple line. Why? Because this purple line represents the tie line, and again a tie line is connecting X and W, and when we have a stage, we have vapor going up, liquid going down. This vapor with composition Y, this liquid with composition X. So the relation between this X and Y is represented by one tie line. So the number of tie lines would be equal to the number of stages. Okay, so how many tie lines we have here? The tie line are the purple line, so this is why it is better to draw a tie lines in different color, so we can distinguish between these lines. So I have, this is first tie line, second tie line, third tie line, fourth tie line. So the number of stages is 4. The number of stages is 4 stages. Okay, and what's the feed stage? The feed stage is the stage where we cross the feed point. See, this black line is the feed point, and we cross it at stage number 3. So the feed stage will be stage number 3. So that's it. This is the Ponchon-Savit method. Now the last thing I would like to mention here is how to determine QR, the duty of the reboiler. The duty of the reboiler can be determined easily using OW point. Remember that when we say OW point as XW and the for y axis it will be HW minus QR over W. Okay, so I go to the graph. See here, this is XW. This XW will have coordinate X and coordinate Y. Okay, so let me do it again. I have here this OW. This will have XW here, and it will have some number here. Let's call it N, a number. Okay, so I read this number here, which is on the y-axis. Of course, this is the y-axis. It is not the vapor composition. This is the y-axis that represents the enthalpy. Okay, so I read this number here from the graph, and of course you know that the top line is H capital versus Y, the bottom line is H small versus X. Okay, so how I can determine HW? Again, HW, I start from XW, and then the cross with this bottom curve will represent my HW. So HW will be this. Okay, so I know HW, and how I can know W? From the overall material balance. Remember the overall material balance? This F is equal to D plus W, and ZFF equal XDD plus XWW. I can get D and W. Okay, so I know HW from the graph, I know W from material balance, and this guy will represent N in this one, where it is, yeah, N, which is the OW y-axis coordinate. Okay, so I will have a number N that I read from the graph at OW from the y-axis. So this is from the y-axis, from y-axis at X, at OW. Okay, will be equal HW minus QR over W. I know HW from the graph, I know W from material balance, I know N from the y-axis at OW. I can use a solver to determine the duty for the condenser, QR. Once I determine the duty of a condenser, this is the end. So the Ponchon-Savit method can determine the number of stages and the condenser duty and the reboiler duty with the help of material balance, equilibrium relationship, and energy balance. So that's it. This is the Ponchon-Savit method. I hope you find this video as helpful for you, and thank you for your listening. I wish you all the best.